design and verification. Okay? So let's talk first about nonlinear dynamics. Okay, so how do we address the nonlinear dynamics of the machine? I want to start with talking about tools we're using for analyzing the local stability of the nonlinear systems. I'm going to try to convince you that if we can just analyze, if we can efficiently analyze the stability of the system throughout controls, there's been examples of being able to efficiently analyze stability leading to then better control design. Bus control, that's certainly true, and lots of places that's been true. So I'm going to tell you quickly about the Lyapunov function-based approach. I have slides, but I think it'd be a little bit more fun if I do it on the whiteboard, okay? So let's do it on the whiteboard. Let me just, how many people think about Lyapunov functions all the time? Yeah? Okay, not everybody. I'll do it. Let me just quickly motivate Lyapunov functions, and I'll get to the good stuff. If you eat Lyapunov functions for breakfast, then bear with me for just a minute, and we'll get back. Okay, so let me just motivate Lyapunov functions. Here's sort of the simplest robot I can possibly imagine. Imagine I have a simple pendulum, okay, with mass m, point mass m, link length L, parameterized by theta in a gravity field, yeah? All right, so I can write down the equations of motion of this really easily. ML squared theta double dot, I'll give it a little damping, plus theta dot plus MGL sine theta equals 0, no problem. Okay, so given a differential equation description of the system, I should be able to ask you simple questions like, if I give you theta at time 0 and the initial conditions and theta dot at time 0, then I'd like you to tell me what's theta for the rest of the time, right? It's a simple, fair question for any differential equation. The embarrassing thing, I guess, is that I can't tell you the answer, right? The simple pendulum's enough to break my ability to analytically solve that, to break anybody's ability. There's no sort of closed form solution. Even if I took the damping out, the solution would have elliptic intervals of the first kind, and it's not really useful. If I put the damping back in, I don't even have anything to give you. Okay, so if we're talking about analyzing the dynamics of our pretty complicated nonlinear machines, that happened right just because of this sign sitting here. If that was just theta, I could just do linear analysis on it, but as soon as that sign got in there, it broke everything. So the prospects look a little grim. How am I supposed to analyze the complex dynamics of a approaching airplane if I can't even analyze the dynamics of a pendulum, right? Okay, all is not lost. There's a couple things I can say about the pendulum very quickly. So I'm pretty sure, for instance, that if I watch it long enough, that the final condition is going to be at the bottom. I'm going to go out on a limb and say that, right? So I think the final condition, theta at time infinity, is going to be at the bottom. And why do I know that?